guys, thank you for coming. And like she mentioned, we're going to focus on optimization and troubleshooting. So a lot of times those two terms are used in conjunction when looking at individual gas lift wells or gas lift fields. So today I kind of broke it up into optimization and then troubleshooting, just to really give it a different segment between each two, because there is quite a bit of difference. And typically when you're troubleshooting, you find some means to optimize, and when you're optimizing, you find some means to troubleshoot. But with the number of gas lift systems installed in the Permian, number of gas lift installs installed in some of the other unconventional plays, it becomes ineffective to really troubleshoot or optimize on an individual basis. So one of the things we look at is really start looking at well selection, going through a list of wells to determine prioritizing the importance on which ones to optimize, and then from there help with some of the troubleshooting. So just to give you a highlight, this is kind of a generic slide, but it illustrates the point that you can increase production from base production even with some of these tight unconventional resources. It's not as instant gratification as some of the conventional high PI areas, but you still can get production increases. You still can extend the life of the well through optimization with gas lift. So, and some of the purposes with optimizing gas lift, the biggest one, of course, is increased production. But a lot of times, especially later life, very tight unconventional reservoirs, that increase in production is very minimal to a well-to-well basis. So we start looking at other things. The biggest one, of course, is utilizing compressor horsepower correctly. Most compressors that are using to supply the pressurized gas to gas lift wells are on rental basis. They're renting them per horsepower, or they're renting them per PSI, how much discharge pressure they can put out. So by being able to optimize and downsize our horsepower, downsize our required injection pressure, we can save the operators money through lower cost compressor rentals, and then also gas volume buybacks that the compressors are using. A 225 horsepower compressor might burn between 50 and 60 MCF a day. So if you have 100 or 200 compressors, which is not uncommon, running on a 3 to 5 year lease term, it's quite a bit of gas that they're wasting due to oversized horsepower in some fields that need lower horsepower operations. Of course, the biggest one, especially right now, is reducing operating costs. Going back to horsepower and reducing the amount of gas we need. And then, of course, if we can lower our capital expenditure, mainly through compressor rentals and purchase, it works better that way. So where do we start? It can be confusing. It can be kind of overwhelming when you have a lot of wells. Do you start at looking at your casing pressures, your tubing pressures? Do we start off on new wells that produce high volumes, or the later life wells that are producing lower volumes? If it's a pumper, do we start with wells closer to the house because they're easy to look at? So there's a lot of different things to look at when trying to do a well selection for optimization. So what we've done is we've broken up a couple different ways to build some basic selection criteria. Relatively easy. It can be done in an Excel sheet. It can be done within maybe an hour or two of engineering tech time to plug in the data to help determine which wells to prioritize. So, and two of the biggest things we look at are we look at the well performance and the injection differential, just to give us a baseline to really select the wells to start optimizing them. We could just lay out a handful of wells and pick the ones we want, but this helps us prioritize which ones should be focused on initially. When we're looking at our well performance, we're simply looking at utilization of injection gas versus return. How much total fluid are we getting back from the well? And the way we prioritize that is we're looking for over-injection, using too much gas to get very little fluid back. and we set those up as the initial or the high priority wells to start optimizing. With our injection differential, very similar. We're looking at the differential between our casing pressure and our flowing wellhead pressure. The injection differential really helps locate facility restraints, helps us determine ways to optimize our surface setup, if it may be flow lines or high pressure separators, ways to improve our surface facilities that will show back in production increases and lower compressor operation. Because if we can, with our injection differential, if we can lower our casing pressure and still maintain production, we can lower our horsepower, we can lower our rental costs with our compressors. So here's just an example slide that we took a segment of 10 wells based off of our total gas injection volume versus total fluid production. And we're able to prioritize them based off of that differential to give us an idea on which wells we need to review first and which wells we need to review last on the list. And so that gives us an idea where to start. We need to actually start with a well that's producing actually the lowest amount of total fluid, but is using one of the highest amounts of total allocated gas for that well. So we look at that well and we determine that's the one we need to start out with, just to determine how much of that gas that we're allocating to this well can be either sold or maybe allocated to one of these lower wells that are using less gas. With that, we add our operating casing pressure and we look at our TID as well to help get an idea in terms of, do we have some surface restraints with some of our lower percentage TID wells like this one? Do we need to look at surface facilities? Do we need to look at adding better infrastructure, better flow lines to get a closer casing tubing or a greater casing tubing differential for our TID percentage? So it's relatively basic. These things can be built in Excel. We use them basically for a individual field or individual operator to really help us get an idea of where to start. It works from 3 wells to when you leave an operator's office and they give you a stack of 25 wells to look at. We can start with this to understand which ones are the most important to look at, to really dive in and start looking at the other tools we can use to troubleshoot and or optimize these wells. So some of the things that we look at after we've selected the wells, the biggest one is adjustment of injection gas. That injection gas requires horsepower. That injection gas, if it's being injected into the well, cannot be sold. So we're either losing money through increased rental pricing for compression or lacking the ability to sell that gas. We also look at reducing or removing surface restraints. Biggest one is undersized infrastructure. Sometimes poor setup of infrastructure is key in removing those things and basically streamlining the wellhead to the central production battery. With that, we also can identify a lot of system redesigns, things that can be changed downhole with the gas lift system to help improve production once 1 and 2 have been adjusted. And of course, adding secondary artificial lift, prolonging the gas lift system that's installed downhole, improving efficiency with what we have rather than going to a different type of artificial lift, primarily sucker rod pumps here in the Permian Basin. So when we look at adjusting injection gas, there's really 3 main avenues that adjusting injection gas is taking place. More times than not, number 3 is the most common. We make an adjustment, we watch the well test, we make an adjustment again. It works, it's very time consuming, it's very manual, but it does get you to the point. 2 of the better ways to adjust injection gas is either through utilizing tubing velocity curves, or through a nodal or analysis program to help determine target injection volumes. So here's a basic gas velocity tubing curve illustrating different gas volumes required for surface pressures and tubing sizes. So something like this can be used as a reference based off of the tubing size and the wellhead pressure to select optimum injection rate. A better way, or a more in-depth way, go to the next slide, is through nodal analysis, generating a deliverability curve and looking at how a change in injection gas affects the total production of the well. So typically, those are the two primary ways to make adjustments on your injection gas volume. Not as typical as just simply making the manual adjustment and seeing what happens, but a preferred way to, I guess, get technical or get scientific with determining injection rates. So the next one is removing or reducing surface restraints. The biggest one is wellhead chokes, especially on these new horizontals. Wellhead chokes are applied, they're set to a certain degree, and they're usually left there. Initially, they perform really well when holding wellhead pressure back on a high fluid rate well, but later life, when the well's flowing at lower rates, they become a restriction. So either fully opening or completely removing wellhead chokes reduces that wellhead pressure, increases that differential between casing and tubing. Another one, people are getting better at it, especially with new construction, but removing or reducing the number of 90-degree elbows from the wellhead to the tank battery. Henry Winkler out of Texas Tech used to say that 8 elbows equals a bullpup. And due to the pressure drops, it really does. So taking out elbows, adding different types of flow lines to reduce that pressure loss can be key. And then in some cases where you have high line pressure, you have high production pressure at your central tank battery, utilizing small wellhead compressors, compressor jack to lower that pressure. So here's an example of just by removing wellhead pressure, how you can increase production on a well. So simply by taking off the wellhead pressure, not changing compression, not changing gas injection volumes, how you can increase production on a well with higher wellhead pressure and lower wellhead pressure here. So being able to identify a low percentage TDI can help increase large amounts of production in those wells. So system redesigns. System redesign typically requires a workover or a wireline rig. So typically a last resort means to optimize a well, mostly because this one costs the most money for adjustments in injection gas or facility changes. But typically they can increase production, they can extend the life of the well based off of the parameters. And some of the things we use to determine if a redesign is necessary is a flowing pressure temperature survey. Fantastic for determining flowing bottom hole pressure, identifying injection points, giving us details as to how to redesign the gas lift system to increase production. Adjusting for facility or surface conditions. Maybe it's an exploration area that's starting to build up, so we're starting to see higher line pressures. Different things like that. Interference from offset fracs. So by utilizing or understanding of surface conditions and how they've changed over the years can help with a redesign. Moving an injection point seems to be a big one, especially on some of the deep Permian Basin wells where they're relatively high rates for the first 2 or 3 years, and later life they're very low rates. So by adjusting injection points, by basically deepening our tubing string, we can increase production that way. And then also applying special application gas lifts, below packer gas lifts, different types of systems to improve the efficiency of the well. So looking at redesigns in terms of flowing pressure temperature surveys. So here's an example of a well that had a flowing pressure temperature survey ran, indicated by this purple line here. And that line indicates where we're currently operating versus where we should be operating based off of the blue and red lines. So our blue and red gradients indicate that we're operating less efficiently than we should. So that's a good sign that shows us where we are versus where we could be and how a redesign is necessary to get us to where we are. And this differential, this change in bottom hole pressure illustrates a production increase. So this example here would increase our total production, would extend the life of the well on a gas lift system just by a redesign. Moving our injection point deeper, setting our tubing deeper into the well is a big one, especially with the deep, and by deep, I'm talking 10,000 plus feet horizontals here in the Permian Basin. So this example here was set up initially for high fluid producing, very high reservoir pressure. 3 years later, the total fluid had reduced, the bottom hole pressure of this well had reduced, and our injection point needed to be deepened into the well. So the system was pulled, this system was removed from the well, and this system was installed, bringing the well back on production, being able to carry the well out to a lower total fluid rate later down the life of the well, and furthering the total production of that well. So looking at secondary artificial lift systems as well, this can help extend the life of the gas lift system. This can prevent a workover. This can help operate at lower injection pressures. And two of the biggest secondary artificial lift systems that can be paired with gas lift are plunger assisted and introducing a foam, and I just noticed a misspell, foam or surfactant to increase the efficiency of the system. So by introducing a plunger into a gas lift system, you can reduce your total injection gas volumes, you can reduce your total injection pressure of the system, and then further reduce the compressor needs you need for the well. By adding a surfactant, you can reduce the injection volumes as well by reducing the friction in the flowing tubing. So those type of things can be small added costs that reduce the total price from a compressor need. With optimization, I like to go into troubleshooting. So with troubleshooting gas lift, you're troubleshooting a system. You're troubleshooting the inlet side of the gas lift system, your gas coming from a compressor, coming from a centralized compression facility, or a high pressure line. Your outlet system is your tank batteries, your separators, your heater treaters, and the flow lines associated with that, as well as your downhole gas lift equipment and production tubular in the well. So typically when you're troubleshooting the well, you're troubleshooting all three segments versus just the equipment that's installed downhole. So when we're looking at that, we're looking at our inlet, our outlet, and our downhole. More times than not, most issues are derived from surface facilities. Typically the biggest one is poor run times on compression, too many 90-degree elbows on the flow lines, and high or plugged flow lines are typically the biggest issues or the biggest constraints that go into troubleshooting. There can be downhole failures, tubing failures, gas lift equipment failures, but it's good to start at the surface on equipment that you can see, that you can touch before moving downhole. So when looking at inlet problems, the biggest one we find is low casing pressure. So this can be identified through our TID matrix by looking at that low percentage and understanding the low casing pressure versus flowing tubing pressure. And so this is one issue that can be identified through your well optimization. And typically with a low casing pressure, a lot of it is associated with the choke. The choke can either be undersized to reduce cost in wintertime or in high wet environments. It can be frozen. And in other areas, especially new construction areas, the chokes can get plugged. Typically, welding debris, metal shavings, those type of things tend to plug up the chokes. Checking gauges. This is very common in older areas. Areas that, what we call our marginal areas where they're really watching LOE calls. So they might have a gauge that has been moved around from 3 or 4 wells, or has been riding on a pumper's bed of his truck for the last 6 months. So inaccurate measurements through either gauges or through pressure transducers if it's a SCADA system. And then also checking back pressure regulators, making sure they're not plugged. So essentially with low casing pressure, we're looking for a plug in the inlet side. The other one is high casing pressure, the exact opposite. So typically these come from over-injecting, oversizing your chokes, oversizing your injection lines, increase your high casing pressure the most. Very similar to our low casing pressure, we can identify this through our well selection and make a note that outside of optimization, we need to troubleshoot this well based off of a low or a high casing pressure. Restrictions and tubings, again, different things like restrictions and oversized chokes can illustrate these high or low casing pressures. So low gas usage, another one that can be identified through our optimization is a big one, especially when there's production in the ground that is not being removed. So by using or by having a low gas usage, we're not lifting all the fluid out of the well that could be lifted for this well. So looking at things like your injection meters are accurate, making sure your compressors are running, checking again for plugging in the chokes are the key things to look at with low injection volumes. And again, these are all surface issues. These are all things that a pumper or a roustabout crew can get their hands on and identify relatively easy just by going from compressor to wellhead. The other one is excessive gas usage. So usually coming from leaking or holes in the flow lines or close to the wellhead, over-injection from the systems in general can use more gas from an individual compressor or from a field and cause some issues with higher runs on our compressors, will also revenue through our sales gas. So with that, we like to look at our choke sizing, controlling how much injection gas we can, and really making sure those adjustments are key to our optimization side of the system. Also looking at gauges again, our facility gauges, our gauges on our compressor, to understand that the numbers that the gauges are showing are what we should be reading for the system. So without outlet issues, the biggest one is pressure. And pressure due to restrictions. Undersized flow lines, too many elbows, too many 90-degree bends within the well are typically the biggest problems with outlet side. So typically when reviewing outlet problems, we just like to do a full system review. We'll understand what's the need for flow line size, what's the distance between the flow line, and some of the things that can cause issues. Restrictions are typically the biggest one. They can be through solids like scale and paraffin, or they can be through hydrates and ice. So, and looking at our separator operating pressure, switching systems over to low pressure systems is key to get that overall system pressure down. If we can get that overall system compression down, we can get our compressor size down as well. Now downhole problems. Downhole problems do occur Downhole problems are a little trickier to identify because they're downhole. We can interpret the information, but we can't exactly see what the problem is. So we have ways to understand that. We have ways to identify what kind of downhole problems can occur. So the biggest one, basically just circulating gas. We're injecting gas into the well, we're getting the gas back, but we're not producing any fluids with it. Typically that's associated with a hole in the tubing, a hung gas lift valve, a leaking point within the system that's allowing gas into the tubing above our column of fluid. So checking for holes in the tubing, checking for plugs in the tubing are the biggest way when you identify a problem by circulating injection gas. The next one is the well not being able to inject gas into the well. This one can be tied to some surface issues, some inlet issues, like a plug at the wellhead or a plug at the choke, but it can also be caused by occurrences downhole, plugs in the gas lift valves, a bridge across the casing and the tubing that prevents the gas from being injected into the well. Flowing in wellheads, well slugging, very common with horizontals, can also be occurred through under-injecting or over-injecting in the well. So as we've gone through a lot of the troubleshooting issues are tied back to optimization. So again, this can be identified through our optimization selection because we could be either over-injecting or under-injecting the amount of gas that we're utilizing for the field. So wells not producing, wells not unloading, basically we have a dead well in our hands. So this again can come from a couple different conditions within poor design, a design that was designed for lower fluid rates than what the well can produce, a change in well conditions and change in water cuts, formation gas volumes can cause these issues and force a workover to be done to remove the equipment and replace it with a better performing design. So a valve hung open. A valve hung open can be tied to circulating dry gas. It can be tied to a drop in total gas or total fluid production. And this one's typically caused by debris. Again, we see this one most common in new construction, high active areas where there's a lot of pipelines being put in, there's a lot of roustabout work around the well site. So the biggest culprit is welding slag, metal shavings, those type of things that cause the valves to hang open. In some very salty areas, salt can become an issue. Bakken is a notorious area for salt deposits. Some parts of the Delaware Basin the same way create lots of salt issues, bridging, plugging. Holes in the tubing. So holes in the tubing can occur with new production tubing, can occur with older production tubing, but can really affect the overall system through loss of production and increase in injection gas. So typically the biggest thing is to look for those holes in the tubing once the excessive gas usage has been identified, once the lower casing injection pressure has been identified. And with that, you simply you're equalizing your tubing and your casing pressure, and you're relieving the casing pressure to see if you have communication from tubing to casing. So those type of things do help to identify downhole issues by reading surface gauges. Another way is what we call a PSC test, testing the operation of the gas lift valves. So looking at what the valves open and close at and adjusting our injection rate to identify where we're operating based off of surface conditions. So a very simple operation typically lasts about 30 minutes on location, where we can simply turn off our injection gas, shut the wellhead in, and allow our casing pressure to equalize out. And where that casing stabilizes out, gives us an idea of what depth of the well we're operating at and what conditions we can expect with the system in place. Valve spacing too wide, valve spacing too high goes back to the optimization side of deepening our injection point, getting a better system by a workover. So some of this you can fix without a workover, either through utilizing a secondary injection point like a nitrogen cryogenic or a membrane nitrogen unit, or swabbing the well. In most cases, though, it does require a workover to help improve the system of production. So with that, tuning the well, making adjustments, adjusting a well that after you've troubleshot, you're ready to get back on production. So one of the things with continuous flowing wells is they usually use more injection gas when they're new versus when they're older. And what happens, especially when pumpers are busy, they set the injection gas volume and they walk away. They go and they check on other wells and they forget to change the injection gas volumes. And with horizontal wells, the rate of decline is relatively quick, usually 90 to 120 days. You can cut production in half based off of the deliverability of that well. So if an operator or a pumper set the injection rate for a high fluid rate, and 3 or 4 months down the road it's half that production rate, the injection rate needs to be adjusted. Something that can be identified through optimization and can be changed in an incremental fashion until you get your optimized injection volumes. And some of those things can come through your tubing velocity curves and through nodal analysis as well. Thanks. I jumped the gun there, that's okay. And with that, these are some of the tools we use. We mentioned reading our surface casing and tubing pressures to get an understanding if we have a hole in the tubing, if we have a restriction downhole, based off of our tubing casing pressures. Getting measurements of our lift gas. Getting measurements of our lift gas is huge in both optimization and troubleshooting. It can help us get a better idea on how effective our system's operating, and it can also give us an idea if we have issues downhole. Some of the other tools that we use to collect data, I guess you could say the cheapest and the easiest is computer calculations. You could put in different scenarios with the models and allow it to give you an idea as to where you should be operating and how you should be operating with the system. Running pressure temperature surveys is probably the best in terms of it gives you real-time data downhole that identifies how the system's operating. And also determining fluid levels is very helpful. So measuring gas volumes, as I mentioned, very important, very good way to help optimize and understand really how efficient your gas lift system is. With that, a good accurate well test is important, especially when operating in these centralized tank battery systems. Doing monthly or in some cases weekly or daily well tests are key to really improve efficiency across the field. And well tests typically involve surface casing pressure, our flowing tubing pressure, our total fluid producing rates, what exactly are we injecting, and checking those injection gas volumes. Making notes about sand production, making notes about paraffin. Paraffin is a big issue. Salt buildups, hydrates, those kinds of things. And really looking at or getting an inventory of what you have out on location. Flow line chokes, choke sizes, flow line sizes. The last few years there's been a lot of turnover, a lot of acquisitions, small operators, equity-backed operators selling to other operators. Poor inventory of what kind of equipment's out there. So a lot of operators take that for advantage. They don't realize what they have. They assume it's similar to their base operations, when a lot of times it's not. It might be undersized for injection chokes. They might be oversized. They might be utilizing something that they could take from one well site and bring to another to lower costs and help prevent adding inventory to their wells. So really making notes of equipment inventory on location goes a long way with the well test and full field optimization. Computer calculated generated curves. These are really simple. Depending on how many you're asking for, 10 or 15 at a time, it takes the computer less than a few seconds to generate these for you. But it's good information you can use across the field. And when we're looking at that, we're basing this information off of our well test. We're basing this off of our measured gas volumes to get an idea of where we're lifting with the system versus how we should be lifting with the system. Fluid level determination, very helpful tool, very inexpensive tool that most operators have right around the truck with them. So you can determine bottom hole pressures with flowing fluid levels. You can determine where you're lifting with fluid levels, and then you can help with some problems, either holes in the tubing, holes in the casing, plugs in the tubing through a echo meter or a fluid level shot. Of course, the best one is a pressure temperature survey. Pressure temperature survey gives you real-time information downhole of how the system's operating. And you can take that information to improve a gas lift design, adjust injection rates, adjust surface facilities to maximize that flowing bottom hole pressure. So probably my favorite is a pressure temperature survey. I'm not sure on cost, but it does require some well intervention and a little more money versus some of the other services that can help improve efficiency, but one of the best ways to improve efficiencies in gas lift systems, or really any type of flowing well. And some of the ways that once you've identified a well that needs to be troubleshot, once you're ready to fix an issue, we have a couple of different procedures on how to fix those issues, typically surrounding plugging or hung open gas lift valves. So performing a PSC test, probably one of the quickest, easiest ways to determine operation of the system. And it typically takes about 30 minutes of overall work to determine this. And what you're doing is we're simply turning off our injection gas. We're allowing our casing pressure to bleed down to typically surface facility, or in some cases atmospheric pressure, and we're seeing what our casing pressure stops at. It should stop at a given or a known casing pressure, and that known casing pressure tells us how the system's operating. If it's operating too high, if it's operating too low, or if it's operating with any other type of restraints, typically in the tubing. Rocking procedure. So this works very well for hung open valves, for debris stuck in the gas lift valves downhole, and trying to remove that debris without removing the production tubing. And essentially what you're doing is you're creating a large differential between your tubing and your casing, and you're forcing that debris out of the gas lift valves. And just a highlight of the gas lift equipment and where some of those debris can collect around this area here or through the lug that typically cause the biggest issues with a gas lift system. With that, I think that's it. You guys had any questions for me?
Can you use service pressure gauges as well for your troubleshooting?
You can, yes. Typically we like the data pole that take 15-second, 5-second data collection for 24 or 48 hours. Actually prefer using those with a pressure temperature survey in conjunction.
What about like spider gauges for you?
Yes, we do. Yeah. We use those a lot with operators that lack SCADA systems. So we can go put those out 24, 48 hours and get quite a bit of detail through that. Yeah. Well, guys, thanks for coming out.
Any other questions? If you'll join me in thanking Matt.